Oh, Jesus. Hello. Hello, can you hear me?
Good afternoon. Yes, ma.
Okay. I was even just wondering with this thing because yesterday I was really, how will I put it, kind of frustrated because I know I earlier on said we'll have class um 7 to 8, but I came online. I don't know what happened to the e-learn platform. It won't allow. So I'm just happy today it allowed. I'm just thinking maybe because I saw there uh, 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 kind of a schedule notifying about this class 5 to 6. So I don't know how it's controlled. Let me minimize this to get my PowerPoint so that we can go straight ahead. It's just that I don't know if everybody's aware of this, as you people are meant to be much more than these. So just a little while, I'm coming. Okay. Oh, yeah, I think I've gotten that. All right. Okay. Well, without wasting time, we'll just start. So I'd like to welcome you to our class today. Last week we had we treated Module 1, Unit 2, and we've covered that. Today we're going to look at Module 1, Unit 2, because we treated Module 1, Unit 1 on Tuesday. So I would begin to share my PowerPoint here. Have a lot of things on this. Okay. No. Okay. That should be it. Can you see my screen?
Yes, ma'am.
Okay. I believe you can all.
Yes, ma'am.
All right. Okay. So during our previous lecture class, rather. Okay. Can somebody just recap, what we did last week? Just, this is an interactive class. I will not be doing the talking alone because it wouldn't be good. That's not the way learning goes these days. Learning these days is learner-centered. Who is that one that you started? You want me to begin to mute? That is Ismaila. Ismaila, please mute yourself. Ismaila Abdulmumuni.
I'm not.
Mute yourself. Okay, you're not talking. Where did that noise come from?
I'm not the one.
Okay, so I
I'm not
don't
the
know.
one.
Do you people want me to begin? This thing will disturb this class, and I don't have time for that. So please, like I said, this class. Do I have to mute everybody? I think I should mute. I don't want to be muted because how will you talk? Now I want somebody to talk. Like I was saying, this class, facilitation class is meant to be student-centered. I don't have to be talking alone. You won't learn like that. And you won't learn to remember like that. It's supposed to be, there's something you've been reading and have taught. So let's recap. Somebody should just like summarize what we did when we met on Tuesday. Anybody, just all of you, but when you want to talk,
I
please.
about periodic table last week.
Mm. Hmm?
We learned about periodic table last week.
Hmm?
So you say you can answer question.
Yes, ma'am.
If you ask question.
I'm listening.
About the arrangement of periodic table and how it was organized, how it was arranged by Dr. Mendeleev and
Okay. Yes, other contribution. We're here to just study. It doesn't mean that you must at least say something. It will even help you to know whether you understood, whether you have learned, and all that, because you will not know what you know till.
Okay, good afternoon, ma.
Good afternoon.
Yes, ma. Last week class, I learned about classification of elements, and
Okay.
I learned that the first person to do classification of elements was Anthony Lafossa.
Exactly.
Elements into melter and non-melter, but it was rejected because of metalloid properties. I can't remember the other classification. So another scientist that also classify elements is J.W. Dobarena, and
Yes.
he classified elements into triad.
Yes.
But his own too was rejected. And also, I remember John Newland. He was the one that has a law of octane.
Yeah,
So,
of octane.
yes, ma. But it was the classification of symmetry Mendeleev that was accepted. Due to the classification of the physical and the chemical properties. And when he classified it, he classified it through, is it prediction or how you put it, how he classified that? He put some spaces that some elements will be fixed in, and after those elements will be detected, they fit into those classes. And he's the one that has the law of periodic table that says that elements is being classified by the value of the atomic weight. So I think these are things I can remember I learned in the previous class, ma.
Okay, you have tried, you have done beautifully well, and even the first person that spoke, people have done beautifully well. Any other person?
Yes, ma'am.
Okay, please talk.
Good afternoon. We also discussed about the Mendeleev periodic law.
Yeah. So what did the law say?
He said, the law said,
You can say it in your own words, so that's learning. Just say it the way you understand. I'm not able to mute because I want you to contribute, but let's okay.
Hello,
You all have done well. Yes.
Good afternoon.
Good afternoon.
I learned about the scientists that attempt to classify the element. You told us there are 6 scientists that attempt to classify the element. The number 1 is Antonio Lavoisier, and
yes.
In the year of 1789. And you tell us the reason why the classification did not hold due to the knowledge of metalloids. And
okay.
Good afternoon, ma.
Good afternoon.
So I learned that Mendeleev, even though he's considered the father of the periodic table, he's not given all credit because he also used some past chemists who did research their whole life. He also added that to his own knowledge, which is why he's not given full credit of the periodic table.
Okay. Fatima Imam Ibrahim.
Yes, ma'am.
Yes. You raise your hands. I want you to talk.
Yes, ma'am.
Okay.
So I also learned that
Okay, let me now summarize so that we can move ahead. All of you have, spoken very well. It shows you have learned and you have really tried, and that's the essence of all this. So that even when you read, it will just be, So we began talking about, you see, everything in this world is made from elements. Even this, let me even begin from the human body as we are, starting from my hair. The natural hair is protein itself, keratin. We add keratins. They are proteins, and these proteins are made up of the elements carbon. Abbas, is it Abbas? Abi, who is that? Mute yourself. I think I will
Harry,
have to. I have to. Who is
Ma,
that
please,
that is
it's like
disturbing
we
the
need
class like
discipline.
this?
Anybody you are hearing us from, you remove the person from the group so that everybody will be serious with you. Please, ma.
Let me just mute all of you. I have to stop sharing this to mute.
Yes, please mute yourself. You are making noise and distracting the class.
I will keep people.
I know you can't hear me now, even though I hate to do that, because that's not the way this class is meant to be. That should just be talking, 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 talking. It's not right. Hello?
Hello, ma.
I'm coming. I
Today is my first day of starting these lectures, so I want to know briefly about speakers, please.
Please, can we get any WhatsApp group for this course, please?
Wannan mai tambaya amsar shi ne ba shi da kyau. Namiji duk wanda
Is there any WhatsApp group for this course, please? Someone should drop it so I can join. Thank you.
I'm not on the WhatsApp group, that's why. So I want people to join the WhatsApp group.
Okay. Well, I can't hear you now because I've muted you, but you hear me. In as much as that's not the way a class should be, but many of you are behaving irresponsibly. How can you enter a classroom you want to learn and you're there unmuting yourself, talking? How good is it that I will just be teaching, talking, and you are not talking? That's not how learning goes. It's not like that. I always teach this class, and people respect themselves, so that I shouldn't mute you. So at any point in time, I want to ask questions, even as I'm talking, you can always say you ask questions. How are you going to do that now? That's not good. You did it last time, and this, I'm not really happy about this. Anyway, let me just go ahead. Now, even if you're not hearing, you cannot tell me you're not hearing. I wouldn't know. So it's as if I'm just talking to myself. But let me just go ahead, believing that you're hearing me. So, last week, this week, Tuesday, we treated Unit 1, and Unit 1 was just about the periodic table. And there you have beginning of classification and the periodic law. Like as I was trying to say before noise came, that everything in this world, because that's why I try to give you an overview of the course, that everything in this world is made up of elements. The water you drink is made up of the elements oxygen and hydrogen. Carbon dioxide is made up of the elements carbon and oxygen. Even this hair, as I was just talking about, is protein. hard protein, keratin. The name of the protein is keratin, hard protein. And protein is simply made up of the elements carbon, hydrogen, nitrogen, oxygen, sulfur, depending on how they bond. Everything around us. I'm not talking about the clothes that you wear. So I'm not looking at us, within us. Even the clothes you wear, they are polymers. These are all made from elements and all that. Whether it's silk, they are all chemical compounds made from elements. So everything, is it like the paper you use in writing? It's made from plants, and this plant from the cellulose. Cellulose is a higher carbohydrate, what you call polysaccharides. And carbohydrates, we know they are made up of the elements carbon, hydrogen, and oxygen. I'm just trying to just use basic things around you. They are all made of, or they constitute, or their constituents are elements. So, and all these elements, God in his own infinite mercy helps scientists to have idea of these things. And we're saying that when elements were discovered, there was no order. So there had to be order. Of course, when an element is, or some of them were discovered purposefully, so many of them accidentally. And from there, scientists will begin to test this thing I discovered, what is it, and all that, and begin from there. They begin to come about with their physical property. Oh, this thing I discovered, this element is this color, this is the color, this is the weight, this is the density. Those are physical property. Then some of them will now react with another one and begin to give various compounds. Those are compounds. So with that one, they're able to get their physical and chemical properties and all that. So we're saying that at the early stage, when it was just few elements that were discovered, it was first and foremost, just as the people that have spoken, classified as metals and non-metals. But with the discovery of metalloids, elements that have properties that are intermediate, similar to metals and non-metal, and advance in technology of physical and chemical properties, couldn't hold. Then we now talked about the later scientists, Doberene and all that, how you try to classify. We now talked about John Newland, how he tried to use the law of photon. He was even, the first person to observe periodicity, that when elements, because it's even there in some of your questions, who are those first scientists that even noticed periodicity before Mendeleev now came? Because Mendeleev was not just the first to know this, it's just that he was the one that did it, was able, his own explanation was more scientific. That's why it was, accepted and all that. That of Doberene was, he came out with what he called a triad, just arranging them into three like that and all that. And you can't arrange all elements because not all of them, so where we had heavy atoms that could not fit into how he described his own. Then John Newland, now when he arranged in order of increasing atomic weight, was able to see that some of the elements, as they arrange them in order of increasing atomic weight, you have their properties, at a point in time, the property will begin to, repeat itself. At the end of the seventh element, the eighth one will now begin to have property that's like the first one. But he didn't use chemical property. He didn't really explain it that way and all that. So with that one, there was some limitation because it was using music, because in music there's what is called octave of song. So scientists don't want to hear that kind of a thing that you're using octaves and all that. So they wouldn't accept that. Then come Luther and all that one. He used just only physical properties to arrange, physical properties like density, atomic density, and all those to arrange. He was still able to observe some periodicity and all that, but he only limited was he just used physical property. But now, Dmitry Mendeleev, he built from the work of previous researchers, observing that when these elements are arranged in order of increasing atomic weight, it will come a time, the properties will begin to repeat themselves, what John Newland saw before and all that. And with that one, as this property does, because he used both physical property and chemical property of the element, and not only of the element, but also of the compound that these elements formed. So when he was able to, when he observed that, he now saw that at a point in time, some elements and their compounds will now begin to have properties again, similar to some. Like that, there will be repetition. And when that happened, he now took all those, he now took all those, he now took he now put, all those elements that have similar properties in the same, vertical column, which he called the groups and all that. So the elements were now arranged in vertical columns and horizontal. In order of increasing atomic weight, you have them, you have the horizontal, grouping. Then when you now arrange those ones that have both the element and the compound that you formed, those that now have the same physical and chemical property, now put them in the same group, in the same vertical column. The vertical column he called groups, the horizontal, arrangement, which is in order of increasing atomic weight of these elements, those one he called the periods and all that. And one thing again that he did that was, because we're looking at how did he do his own? Because you can't just use physical property. Elements are characterized by physical and chemical property. So you can't just use physical like how Luther Meyer did, but he used physical and chemical property. And again, he now, when he looked critically, he now saw that each element in that periodic table, that the adjacent elements to it, both left and right, that's the element beside it, both left and right, that element have property that is an average of the elements that are beside it, adjacent it, beside it, both left and right. So with that one, even elements that had not been discovered, as he was arranging them in order of increasing atomic weight, assuming he had gotten to element 89, element 90 had not been discovered, he was able to predict the property. Probably, and okay, element 91 had been discovered, but that of 90 had not been discovered, because as they discover it, they determine the atomic weight and everything, so he's able to place it. So those ones that had not been discovered, he was able to predict their physical and chemical properties with the property of those elements that are beside it that have been discovered. And now later on, when scientists discovered those elements, it fitted exactly to his prediction, meaning because science is the same thing all over. You have to hypothesize first that this thing will behave like this. You not test it. That's a theory. You test it, and when it's found to be the same, you begin to call it law. You learned some of this, you learned all these, your O level and all that. So it became a law. That's why he came out with the periodic law and all those things he came out with. So it was scientific anywhere in the world, even today, anybody, and even after so many centuries that he died, elements that were later discovered, exactly that properties he predicted. It's like that because it is scientific. He had already looked, because science is based on observation, then testing, and you're sure of it. They got that result because there are laws that when you look at the properties, both physical and chemical, of the elements that are adjacent to the undiscovered one, it will give you this. So with all that he did, he was able to do things scientifically, because that's what scientists want to hear. When I'm talking about these scientists, most of them are not even chemists too. Most of them are physicists. Many of these elements were even discovered by physicists, because we equally talk about elements and atoms, electrons, protons, and neutrons in physics and all that. So it's not as if you just say, so science generally and all that. And again, when he was arranging in order of increasing atomic weight, he saw that some elements too that had similar properties, but were not well arranged. He now saw that there was problem with the atomic weight calculator. He had to recalculate them and got the accurate atomic weight. So he did things correctly and all that. But then, just as we're going to go into today, so that's why he came out with the periodic law. And that table he formed by, you know, arranging in order of increasing atomic weight horizontally to get which you call the periods, and then fitting elements into, you know, having same chemical and physical property in vertical column, which you call the groups. He called this his table, having uh, uh, um, the periods and the group. He called it the periodic table. And he called it the periodic table because of periodicity. And he came out with the periodic law. And the periodic law is simply that properties of elements, when the elements are arranged sequentially in order of increasing atomic weight, there's observed periodicity in their properties. So that is simply the periodic law. But then there was still some little fault and all that. But he has given the leeway. He had come out with what is acceptable. So, but scientists were still bothered because of what we're going to look at today. Because of, in his periodic table, there were some elements, like in his own period, the Mendeleev periodic table, the first periodic table, the element tellurium has a lesser atomic weight than iodine. But because iodine had properties of the halogens, he tried to shuffle and all that. Let me just come to that part. Let's look at that table. First and foremost, today's topic is Module 1, Unit 2. And I said this Module 1 unit is made up of 3 subheadings. The modern periodic law. You're going to understand why we now have the modern periodic law, different from there are 2 laws, the Mendeleev periodic law and the modern periodic law. We equally have the Mendeleev periodic table and the modern periodic table. We would get that. So we're looking at, we want to look at today the modern periodic law as it is in that your unit 2. Now, I don't know if you can see my PowerPoint here. I said I'm not going to read because I've already said all that I said here. But okay, let me just say, just trying to talk about the anomaly in Mendeleev's periodic table that made scientists to still keep on, you know, trying to unravel the issue. And that issue is when it comes to the elements, nickel and cobalt, and then tellurium and iodine. Now, nickel has atomic weight of 58.693, while cobalt has atomic weight of 58.933. So when you look at this, let me come to where I brought out that properly. I think this, you understand it better. Now, the atomic weight of nickel is 58.693. The atomic weight of the element called cobalt is 58.933. So when you look at these by some fractions, cobalt has more atomic weight than nickel. So if you're arranging in order of increasing atomic weight, nickel should come first. After that, you have cobalt. Then when it comes to the element, iodine and tellurium, iodine has atomic weight of 126.90, while tellurium has atomic weight of 127.60. But in Mendeleev's periodic table, so when we look at the atomic weight, since he arranged it in order of increasing atomic weight, it means that tellurium, it means that iodine, 126.90, should come first. After that comes tellurium. But in modern Mendeleev's periodic table, as we're going to see, I don't know if, are you seeing it? You can't even talk now because of what you have done. But then it is clear. If you look at this Mendeleev's periodic table, you will see here, let me, you will see here cobalt 6058.9. Following it, because I don't know if you can see, following it is iodine. Sorry, following it is nickel. Then now, this is tellurium. After tellurium comes iodine. But it shouldn't be so. Look at iodine is 127, as we look at 127.60. Why tellurium? Let's go back to that so that you can follow that. Why iodine is 126.60, as then tellurium is 127 point whatever. So iodine should come first. But here you can see that iodine is coming before, tellurium is coming before iodine. Let's just say there was some little manipulation here, just to, because why? Iodine belongs to the group of elements called the halogens, because it has physical and chemical properties similar to the halogens. So he just fitted it there. Now that has negated, when you say it's arranged in order of increasing atomic weight, but every other thing fitted. So, but the issue of this tellurium and iodine, then cobalt and nickel was an issue because nickel should come before cobalt. So, but other things were okay. So scientists still accepted that. But then they can't just go to sleep because something is wrong. They now have to look for a more appropriate fundamental way of explaining this. And this was unraveled by the scientist called Henry Moseley. He's a physicist. So Henry Moseley, much more later, after all this 18 this, 18 that, in 1913, after the discovery of the neutron, now looked at that the atomic weight of an element is simply an addition that is made up of the protons and the neutrons. And now that the more fundamental way of arranging this periodic table, the elements, is in order of increasing atomic number. Because the atomic number of an element is simply the number of neutrons that it has. So based on, the atomic number is simply the number of protons that an element has. So he looked at that the more fundamental way of arranging this periodic table is according to atomic number and not atomic weight. Atomic weight is the number of protons and neutrons. Remember that when all these physicists, like in your O level, when you study the discovery of the electrons, the discovery of protons, the discovery of neutrons, you know how they were discovered from your physics O level and for your chemistry O level. And we say the weight of an atom is due to the weight of the center. And at the center of an atom, you find the protons and the neutrons. So the atomic weight is just the weight of the protons and the neutrons. But the atomic number is just the number of protons that an element has. So he looked at that the more fundamental way, based on different, observation and analysis carried out, that it is better to arrange this element in order of increasing atomic number. That is in order of the increasing number of protons that an element has. So when that one was done, it was able to solve this problem. I don't know if I was able to extract that. Because I said when we order atomic number, because the atomic number of nickel is 27, while that of cobalt is 26. So 26, the cobalt, will come before that of nickel, 27. While the atomic number, the atomic number of tellurium, is 52, while that of iodine is 53. And of course, 52 will come before 53. So it means a tellurium with atomic number of 52 can now be correct to be grouped where it is grouped, and iodine can now perfectly fit in to the group of the halogens. Then that of cobalt. Cobalt is 27, while nickel is 28. So cobalt, when you arrange 27 and 28 comes, that's in terms of atomic number, then cobalt will come before nickel. So that I want to come to that arrangement when, okay, no, this is, but anyway, you can still use this. Now, this is not the Mendeleev's periodic table arranged using atomic weight. This is the periodic table that was now arranged after redefining the way the periodic table should be arranged in order of increasing atomic number and not order of increasing atomic weight the way Mendeleev did it. So when you look at this table, you can see cobalt is coming first because it has atomic number of 27. Then nickel comes following it because it has atomic number of 28. Then tellurium here, I don't know if you're seeing what I'm pointing here, is now properly, of course, without any discrepancy or any headache. It's exactly where this atomic number explains that truly it should be here. So in this group 6, with atomic number of 52, then following it, iodine, atomic number 53, is now correct, being in group 7 as the other halogens. So with that one, we now have the modern periodic table and the modern periodic law. So the modern periodic table is arranged in order of increasing atomic number, while the modern periodic law says when the elements of the periodic table are arranged in order of increasing, arranged sequentially one after the other in order of increasing atomic number, there's observed periodicity in their properties. So the difference there now is atomic number and atomic weight. Atomic weight of Mendeleev and then atomic number of Henry Moseley that gave birth to the modern periodic table. So you have to know that difference. So with that, we have done subheading 1 of Unit 2, because I said this heading has 3 headings. The modern periodic law, then we have the short form and the long form of the periodic table. I will stop here to take some questions because I can see hands raised. And that's why I don't want to be doing it, because if I go back on meeting everybody, if you begin to do all those your noise, I will not even listen to anybody. I'll just meet everybody and talk and do, because I can't continue doing this. How will there be audio when let me mute you. All right. You can talk now. Somebody raise hand. Neka. I have 2 people raising up their hand. So, sorry, permits me to on this light. It's getting dark here. All right. Neka. Talk after that. Okay, Neka, mute yourself and talk.
Good afternoon, ma'am.
Good afternoon. Good evening.
Okay, good evening, ma'am. I would like you to help me repeat the model periodic law, please. I did not quite get it.
You said you would like me to do what?
To repeat the model periodic law.
To repeat the modern periodic law.
Yes,
but you know the Mendeleev's periodic law. You know that, right?
No, I wasn't in the beginning of the class last week.
I can't go back to that. If I continue like this, we won't go back. Well, the Mendeleev periodic law says Then from that, I will now, so that whenever you're doing this, you just know it's a difference of atomic weight and atomic number. Mendeleev's periodic law says that when elements are arranged in order of what? Mendeleev's periodic law, or the periodic law, says that when elements are arranged sequentially, not sequentially, one after the other, in order of increasing atomic weight, that is observed periodicity in the properties of the element. And I've explained what periodicity is. Repetition in property and all that. At certain interval, the properties begin to, repeat themselves. And that was how he was able to group those ones that have similar physical and chemical properties. As the properties are repeating, he will take those ones that have these similar properties and put them together and begin again. And they begin to, go in order of increasing atomic weight. When it gets to that place, it begins to arrange, it begins to do things like that. Then now, the modern periodic law is saying that when elements of the periodic table are arranged sequentially in order of increasing atomic number, there is observed periodicity in the element. So the difference is just atomic weight and atomic number. Atomic weight in the old one, then the new one, atomic number. Arrangement in order of increasing atomic number. Do you understand now?
Yes,
Do you understand? Okay, and Rotifer. Is it Rotifer light? Yes.
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 Thank you so much for the lecture. I just want to ask, can we get the recording of this lecture?
No, you're not permitted to do so. Rather, even as I started this lecture, is recording. The school itself is recording, and it's for your sole purpose because the school is friendly to you. So at the end, towards this weekend or Monday, I will post the lecture of Tuesday and this one so that you can equally listen to it. Yes, the school has done that for you. So it's being recorded. So over the weekend on Monday, I'll post the lecture. So even those that missed that of Monday, sorry, Tuesday. Why am I saying Monday? That of Tuesday, we get it. Abigail.
Thank you.
You're welcome. Abigail.
Yes, ma'am. Thank you for the lecture. Please, I don't know if you, after the talk, after this one, if you can help me to paste your PowerPoint again, the way you arrange the atomic weights of nickel. Because I missed the one of iodine and the other one, please.
Okay, I will do that. I'll do that.
Thank you,
okay, any other? I'm seeing one hand. I don't know where that. Osai.
Yes, ma'am.
Okay.
Good evening, ma'am.
Good evening. You're welcome.
Thank you, ma'am. My question is, after the elements with atomic number 42,
where did you get to 42?
That's in the box that the iodine is. There's a gap there. So I want to ask, does it mean that there are still some elements that are yet to be discovered?
No, all the elements that Mendeleev predicted has been discovered. Now, that's what we are still going to come. Remember, I said this unit, the subunits. Like when I started this lecture, I said this unit 2 has 3 topics. One is the modern periodic law. Then the second one is short and long form of the periodic table. It means you have not been reading your book, because if you should have read your book up to that extent. Then the third one is nomenclature of elements, with atomic number greater than 1. So now when we get to the, when we get to the element, when we get to the short form, which is the second we want to enter, but I just wanted to entertain questions. When we get to the short form and the long form of the periodic table, you will now get to see that the elements you're seeing in that short form is just few compared to what we have now. So all those things you saw was because of, as of the time, that periodic table. Remember, it was during Mendeleev's time, Henry Moseley in 1913.
Wow.
Well, he now arranged in order of increasing atomic number. But since that time till now, a lot of elements have been discovered. So that's why you're seeing that. So when we get to when you begin to see that one. So, okay, let me take Dada Akesanya.
Yes, ma'am. Good evening, ma'am.
Good evening. Welcome.
I want to ask about updates on practicals.
Okay, practicals. Yes. Okay, thank God. Yeah, you'll be having your practicals. All the practicals 191. That's CHM 191, 192. Physics 191, 192. Bio 191, 192. Then the computer practicals. Yeah, it was actually the message they sent to you people was supposed to be September 25th, but no, I heard today they sent out another message because 25th is already Monday, it's close by. So it's going to take place October 3rd, 3rd of October. That's when it will take place. And let me use this opportunity to finish explaining about it. It's normally done in the 6th geopolitical zone. The school, in its own way, try to make it easy for you to attend because all of you can't start coming to the headquarters Abuja. It's not going to be easy. And where the students' laboratory is in Lagos, they can't start asking all of you to come there. It will not be easy. So they are now trying to, it's normally done geopolitical zone. You know, we have 6 geopolitical zone, north, center, let me say southwest, southeast, south, northwest, northeast, and north central. Now, for Southwest, we use 3 centers: Lagos, Osogbo, and Abeokuta. That's Abeokuta Study Center, Osogbo Study Center, and Lagos. Those that are from maybe even Kwara and all those, they can go to Osogbo because Osogbo is closer to them. So you look at the area that is closer to you, then those residing in the South region, we use the Benin Study Center and Uyo Study Center. Then those residing in the East, we use Enugu Study Center and Owerri Study Center. Those in Northwest, we use Sokoto Study Center and Kano Study Center. Those in Northeast, we use Bauchi Study Center and Yola Study Center. That's where the labs are. Then those in North Central, we use Abuja Model Study Center, Dutse, and then Makodi Study Center. So you have to look at the area that is closer. Like, I know that those that are maybe from that their study center is River State, Benin, what do you call it? River State, Bayelsa, all those things. They go to Tokyo and all that. So that's that about that. So and that your practical is what they will use to grade you in these courses. So if you don't do it, you don't even get a score. So you have to take it seriously. Yes, I've answered Fatima Akisoya. I think I've answered Fatima before. Eh? I've answered Fatima. Okay, Fatima, say what you want to say so that we can move ahead.
Yes, ma'am. Thank you. I wanted to ask what unit we should read up to for our participation.
What you say?
We should read up to where in our course materials, up to unit 3 or 4 for our next.
You will read up to everything, no? You will read up from beginning to end. Questions are picked randomly, nothing like, this is the area of concentration. There's no area of concentration in this one.
No, ma'am, I meant for our next facilitation so that we know what we want to discuss about.
Oh, okay. When you go through your course material, now, you know that this module 1 has 6 units.
Yes,
we have done unit 1. Now today we're doing unit 2. It means that the next one is module 1, unit 3.
Yes, ma'am. Thank you.
And now you have seen only. That's why I'm doing this extra lecture, because I'm not supposed to do this. I'm supposed to teach you once a week. But why I decided to go extra mile, I've looked at that your course material because I've been teaching it before. Now only that module 1 has 6 units. And I'm to teach you for 8 weeks. If I do once a week, it means we'll finish module 1 and then 2 out of module 2. What happens to the remaining module 2 and module 3? That's why I'm just the one offering my services here, just for your own good. So, Eze Abel.
Thank you, ma'am.
You're welcome, Fatima. Eze Abel. You can unmute yourself. Yes.
Good evening, ma.
Good evening. You're welcome.
Thank you very much, ma.
You're welcome.
Yes, ma. You know, I'm still on 100 level, so we just started. So, and like most
all of you here on 100 level, all of you here on 100 level.
Okay, everybody here.
Of course, this is chm101.
Okay. just like the this thing you just mentioned. And me, I'm staying at Niger State. That means my center will be the this thing
Abuja.
that you say.
Yes, that's where you go for the practical. Yes.
Okay. Because I asked.
Yeah. You say I can't hear you.
Ask some of my lecturers like when it's time for the practical. I asked some of my. Hello,
Okay.
man. Can you hear me?
Yeah.
Yeah, I asked a question about the practical. They say if the time is close by, they will inform us.
No, you come to Abuja. It's closer to you. Yes, Kaduna, except Kaduna is closer to you. You go, but I think it's better you come to Abuja. Students from Niger, but we give you option to choose where you want to go. But me, I believe Abuja is closer to you. If you feel Kaduna, I mean, what's it, Kano? If you see Oshogo, but Abuja is closer to you.
Okay, man.
Prosper.
Okay, man.
Prosper.
Good evening, ma. Good evening, ma.
Welcome.
Hey, thank you so much for the lecture.
You're welcome.
I'm staying in Delta State, so the practical is it here in Asaba that I'll join the study center?
Benin Study Center. That's why I said for South, you have two centers, Uyo and Benin. And I think if you're in Delta, Benin is closer to you than Uyo. So I think you should go to Benin.
Okay. Thank you so much.
You're welcome. Osha?
Good evening, ma.
You're welcome.
I really appreciate your lecture, ma. God bless you, ma.
Thank you.
Yeah, quick one, ma. So, I'm still asking my question as regards the practical. I don't know if there will be a calendar for this practical because graduation for someone like me that are working, I don't think it will be good for us to keep coming every day like that and for weeks like that.
There'll be a timetable. There'll be a timetable. Okay. You'll be given timetable. Okay, if they have not even sent it out already, you will have timetable. I believe by next week you will get the timetable.
That's fine.
You will definitely have timetable.
Thank you very much.
Thank you. You're welcome. I'm seeing this one doesn't have name. It says 535991. Oh yeah, talk so that we can move ahead. 535991. You don't have name. So talk. Let's go. Time has gone. Okay, Smiler.
Good evening,
Good evening, welcome.
My own question is, I don't really understand.
You don't understand what? Cobalt is an element. Nickel is an element. So, and I was saying that those two elements, cobalt, nickel, tellurium, and iodine, they were the fourth when it comes to Mendel's periodic table. He did everything right. The scientists accepted. And that's why, and he is the one that formed the periodic table and periodic law. So all those credits are given to him and gave the world the way they should follow in arranging the elements. But though he has done everything okay, there was still a little fault. And scientists want everything perfect because you must explain nature perfectly well. There's no comma in it, otherwise things will go disastrous. So I'm saying when he arranged his elements in order of increasing atomic weight, every element fell into place according to their physical and chemical properties. But when it came to the element cobalt and nickel, follow. I'm going to share the slide again, as somebody now said, because of the atomic weight. When you look at the atomic weight, ordinarily, nickel, cobalt should come before nickel. But he had to, just to let it be that this thing follow the elements that are in the same atomic, that have the same physical and chemical property with it. He neglected that order of increasing atomic weight and just arranged them just based on physical and chemical property. The same thing when it comes to tellurium and iodine. The atomic weight of tellurium is greater than that of iodine. But just because iodine, you know, iodine is halogen and it belongs to the group of the halogen. So it has properties and physical properties and chemical properties similar to the halogen. He's just fitted them. He fitted that one there. So that he's, do you understand? So, but that was why, even though he has done everything well, scientists were like, okay, yes, we have a leadway, but there's still an issue. We can't just relax. Till Henry Moseley now looked at the atomic number. And the atomic number is simply the number of protons an element have. And like when he now looked at it, if you arrange it like that, then it would, like cobalt has atomic weight of 27, while nickel has cobalt has atomic number of 27, while nickel has atomic number of 28. So definitely now cobalt can rightly come before nickel, putting them in that, you know, group that they belong to, that they have the same properties, physical properties and chemical properties with other members of their group. The same thing when it comes to tellurium and iodine. Tellurium has atomic number of 52, while iodine has atomic number of 53. So that tellurium can now come first with 52, then after the iodine. So it was perfect. So with that one, that stress, that headache to scientists was resolved. And when we are now having a new arrangement, no longer in order of increasing atomic weight, but in order of increasing atomic number, definitely the definition will change. The law too will have to change. So that's why there came about the modern periodic table and the modern periodic law. Do you understand? You're welcome. I'm seeing Zubairu. Zubairu, ask your question. Zubairu Abdullahi.
Yeah, all right. Thank you, man. My question is that, you know, we have more than one study centers here in Abuja.
Yeah, that's why I said the one that you use. No, listen to me.
Yeah,
no matter your study.
Are we going to our study centers?
Listen to me. I told you that you people, North Central is going to use Abuja Model Study Center, DUTSE, and Makweki. So for all of you in Abuja, nobody will come to your study center and be saying they are doing. Do you know how much those practical costs? It costs so much to buy reagents for chemistry and everything. It's not really, even in many other universities, what number of practical do they do? So they can't come and be doing it at each study center. It's damn too expensive. So for all of you there in Abuja and North Central, like the people from Niger, those that is closer to, you go to Abuja Model Study Center, DUTSE. I've answered your question, right? Okay, Solomon, Friday. Somebody is saying, what are people in Lagos? Where are we going to? People in Lagos, sorry, let me just answer somebody who just sent it in the chat. They said, how about people in Lagos? People in Lagos, I told you that for Southwest, we have Lagos, Abeokuta, and Osogbo. So if you live in Abeokuta, in Lagos, and you feel that Abeokuta is closer to you, go to Abeokuta. Then if you want to use, because you know the laboratory in Lagos is at Ahmadu Bello Way. That VI, Ahmadu Bello Way, the study center there, that's where it is. So you choose where you want to go. So somebody said, specific date. I told you it will start October 3rd. You say, how about people in Kwara? People in Kwara, like from my knowledge, from what I know, people in Kwara go to Osogbo because Osogbo is closer to you. But if you feel you want to come to Abuja, because Kwara is in North Central, if you feel you want to come to Abuja, fine. But I know that people in Osogbo prefer to go to Kwara because it's closer to them. So that's why you look at the area that is closer to you and go there.
Good evening, ma.
You're not starting the practical on Monday, Abubakar. You're starting October 3rd. That's why I told you for there's a counter. They've sent out a counter notice. That's September. It cannot start.
Hello, good evening, ma'am.
Okay, so let's continue with our lecture. If you want to ask about practical, I'm done with it. Who, if you know his question regarding this course, fine. Madonna.
Hello.
Yes,
Hello,
Madonna.
good evening. Hello, good evening, ma'am. Please, I have a
Start.
question, ma'am.
What's the question?
Yes, ma'am. You mentioned something about we're all 100 levels to 100 level students, but I'm 200 level studying public health.
Oh, okay, no problem.
Am I still doing practicals?
So, are you in your course you're doing? Are you to do 191 chemistry 191
No,
192?
My chem is 101.
101. Then you're not to do the practical. It's for those that have it as their course. Okay.
Okay, ma'am.
All right.
Okay, that's what I just want to find out. Thank you, ma'am.
Okay. So any other question during this course otherwise, because time is going, time is going. I'm looking at my time. It's already 6. 1 hour gone. Rhoda. Hello?
Good evening, ma. The person that asked about good evening, ma. The person that just asked about 200 level public health students that are enrolled.
Okay.
That's the same question I wanted to
That's
ask.
all right. Deborah.
Good evening, ma.
Deborah.
Good evening.
Yeah, say what you want to say.
I wanted to ask you said something about group and period.
I can't hear you.
I say, can you hear me now?
Yeah.
Can you hear me?
Yeah, talk louder.
Okay, so you said something about group and period in periodic table.
Yes.
I want to ask, how are they arranged? Are they arranged according to their atomic number as well?
Yes, they are arranged in order of increasing atomic number. What you will do now, get Google the modern periodic table, then be looking at the numbers they put, the atomic number. Even we'll still look at it now. You'll see that it's in order of increasing atomic number. Whether it's, even though it falls into, the group just puts them having similar, for instance, having similar property and chemical, like now, for instance, group 1, all the group 1 elements that are arranged in that group, that same particular column, they have the same property. We know that group 1s are electropositive. All of them have 1 electron in their valence shell, and they are ionized by electron loss and all that. So we have idea. They are oxidizing agent, so they have similar properties, all of them. Then we know that from your secondary school, you know about the halogens and all that. All of them there, they are highly electronegative, they accept electron, they are reducing agent, and so many things like that. So all of them like that. So when okay, now let me continue, because if I continue entertaining your questions, I will not live here. In as much as this is an informative class, and this presentation are meant to, clear your mind. Yes, let me look at answer. Inua, you're raising your hand, so be fast.
Yeah. Good evening, ma'am.
Good evening. You're welcome.
I'm in 200 level of public health.
All right.
You are taught on practical. Are we part of the practical?
I think you don't have any, maybe chm101 physics 1, all those kind of things. You don't have it as a course, right?
Yeah.
Yes, once you don't have any of the practical course as a course that you're meant to register for, so you don't have to do it.
Okay.
Do you understand me?
Yeah, I'm clear, ma.
Mustafa. Yes, Mustafa. Yes.
Okay, Ephraim on the line. Ephraim. Hello, my Ephraim on the line. I want to appreciate, because I was still doubting the reader in the 200, still going to go and do practical again. In respect to that.
Just so far is not in the course meant for you to do. You didn't register for it. If you didn't register for it, you don't have to go and do it. So Mustafa.
Thank you.
Please be fast. Mustafa, you are raising up your hand. You're taking our time.
Is not
Okay, I saw Akachuku or something like that. Akachuku? Is it, I don't know. Okay, in the absence of that, let's go back to our Emmanuel de Santos. So yeah, talk, sharp.
Hello, ma. Good afternoon, ma.
Good evening, welcome.
Good evening, ma. Please, I wasn't in the last class, last facilitation, but now going through my materials, I saw references like triads in under this one that discovered some of the elements triads, and it wasn't explained in the materials, ma'am. Please, can you go
Is
in
explaining
bits
your material. Is explaining that. Is in that.
octaves?
No, I will not go back there. I will not go back there. You'll be taking me back. We will never move forward. If you were not there, I don't know where I sent out this message. People came, so I don't know why you didn't get it. And it's there in your course material. I'm only just.
You can go back to the record.
Yes, I'm only just trying to simplify it here. But be that as it may be, because it's our own. We would like to attend to every student. So, like I have said, that over the weekend on Monday, just listen. That over the weekend on Monday, I will post. Even this lecture we're doing is being recorded. I will post the recordings of the first lecture we had and this one, so that those of you that were not there during the class, you can listen to it. Even this one again, you can listen to, because we recapped it. Before we started this class, we explained it again and all that, although not vividly. But when you listen to that first class, you will do. So by Monday, just by the time you go, let me say by Tuesday, by the time you go to the virtual learning environment for this course, the e-learn platform for this course, and when you just look at, is it instruction, not instructional video now, recordings, facilitation recording, you will see it there. So let us go to move ahead, because we have only just succeeded in doing one of the whatever. So we are done. But I promised somebody I was going to, because somebody, I can't even remember who that is, said I should, he wants to see, this part. I don't know if that person is there. I can't remember your name, but I remember somebody said you would like to see.
Thank you.
So this is it. I don't know if you're trying to copy it, so you can just be fast. I'll just give you a minute to do that. It's a minute, so don't waste my time.
We're inside now.
I'm done. Thank you.
All right. So now we are now going to the. You see this human being. Okay, I think I would maybe is it meet you again? We want to look at the second subhead of this unit, which is the long form of the periodic table. Before I now come about that long form, or before we go into look at this periodic table, this is the short form of the periodic table. This is the short form of the periodic table. But this one is Mendel's own, but I'm going to bring to you the one after the work of Henry Moseley. So this is it. This is the short form of the periodic table as of 1930. After 1913, we started arranging it this way. So, like you can see here, like somebody was saying something about atomic number, whatever. So, okay, if the atomic number, is in order of, is it increasing atomic number? There's something, I can't remember what that person asked, whether it was talking about something about physical and chemical properties. So I just said whether if you arrange it, okay, he said whether if you arrange it in order of, using physical and chemical properties, whether it will still be arranged in order of atomic weight. And yes, it is like that. You can see it here as it arranged. This is hydrogen, helium 2, lithium 3, beryllium 4, boron 5, and like that. And it keeps on going going 10, 10, like that, 15, 17. Just say it. It's arranged in order of increasing atomic number. That's how the periodic, the modern periodic table is arranged. And this is the short form as of that time. But later, as more and more elements were discovered to fit in the gaps, even more gaps than he put and other, but they were all able to explain it based on his work. That now brought us to this long form of the periodic table. And that is what we have till as we are talking now. This is the way the periodic table is, the long form, because of discovery of many more elements, and all of them are arranged in order of increasing atomic number. You can see the atomic number there, those numbers you're seeing on top of them, you know, in the box where you have the elements and all that. Those are the order of increasing atomic number. Now, there's something I want to say. I said the above, that's the one I've showed you, is a short form of the periodic table, which came after utilizing atomic number to arrange elements. Then in the short form of the periodic table, you have 7 rows. That's seven horizontal rows, which are the periods. Then 8 vertical columns, which are the groups. Let's go to that. So this is it. It has 7 columns. You know what is 7 horizontal rows? You know what is horizontal, like this. Then as it comes down like this, you have vertical. So I shouldn't be explaining what is horizontal and vertical here. So if you count, you have them 7, beginning from where the elements are, not from this group 0, because when you're talking about 0, it's just talking about the grouping and all that. So when you count, you'll see that it's 7. Then when you now look at the number of groups, it is 8. As against the long form. The long form has 18 groups, still the same 7 rules and all that. Now, there's some things what I want you to do. I said the normal, like in the short form periodic table, elements are ranging, but I said the normal elements and the transition elements belonging to group. So now, in this modern periodic, in this short form of the periodic table, how the grouping was done, that was how Mendeleev did it first. Even when it was now still arranged in order of increasing atomic number, that didn't change. The only thing that changed was that order of increasing atomic number. Here, you can see 2 elements in the same group. Like, let me take where you have, that's it, 1, 2, 3, 4. The 4th row, the 4th horizontal row, which is the 4th period. You have K19, that is potassium. Then you have C29, that is copper. Both of them in the same place. Now, Mendeleev arranged his own table having what they call A and B designation. And he equally used the numbering of the groups. He used Roman figures. All of us, at least we've been to school, we know what is Roman figure and we know what is Arabic. Arabic is a normal one, the way you write the normal 1, 2, 3. Why the Roman, you already know. Double I for T, triple I for 3, and all those stuff and all that. So that's the difference, because in the modern periodic one, you use numbers, Arabic numbers. That's the normal numbers. And in that of Mendeleev, in the short form of the periodic table, elements you have in each group, elements that are designated A and B. The elements designated some of you are becoming, if I don't do this, I won't, I'm taking my time to go extra mile. So we are here. Okay, I believe you can see my screen. So I'm saying that in this short form, you have in a particular group or the vertical column, you have elements designated as A and B. Those elements designated as A are what we call the normal elements. Then the elements designated B are the transition and the inner transition elements. So the way Mendeleev did it, then other scientists that followed after him, even after the using of atomic number, they still followed that is designation using A and B designation so that you can have two elements in the same group. That's the vertical column. Then when it comes to the numbering of those group 1 to 7 as it were, group 1 to 8 as it were at that time, what was used was Roman numeral. But in the long form, because we're looking at the difference between the short form and the long form of the periodic table, because that's what is in your course material. So that's why I'm looking at it. I said the normal elements and the transition elements belong to A and B subgroups of a group were placed in the same column. Then when I say the normal elements are elements that are not the transition and the inner transition elements. You will see, we say the transition elements are elements, they include the elements scandium with atomic number 21 to zinc with atomic number 30, yttrium with atomic number 29. Now, let me just use this to, I think I should use this periodic table to show you. If you see here now, the long form has already separated these normal elements. Like here in group 1, group 2, you have these normal elements. You can see this purple color is transition elements. If you're seeing the periodic table, then you now have equally the inner transition elements. These ones that are below, some of all these are the inner. These ones too, group 13 to 17, you have them as the normal elements. Group 13 to 17, based on the color that is showing there, I was trying to begin to call the atomic number, but that one will be a bit cumbersome. That's why I'm just using their colors to now show you. Then there's something else. Let me go back to here so that you can follow it. So I said that the normal elements that the transition elements include the elements cadmium with atomic number 21. This is cadmium here. It's cadmium atomic number 21, all through to zinc, then beginning from this yttrium to cadmium. Cadmium is, then you now continue again with hafnium to mercury. In fact, just this is hafnium. All these one that you see in purple like this are transition elements. You can see it somewhere here. Then you have some of all these ones, like these lanthanides and actinides, they are all called inner transition. The ones that are separated out, that are out of it, they are called the inner transition elements. So we're saying that the way he in that is A and B, both normal elements, the A, all this A, the A designation represents the normal elements, while the B designation represents the transition and the inner transition elements. So we're saying in the short form of the periodic table, you have in a particular group both the normal elements and the transition or inner transition elements. But in the long form of the periodic table, it is not like that. You have them totally separated, as we're seeing here. And that's what we're trying to show, like group 1, group 2 are the normal elements. Then from this cadmium to zinc and all that, you have them as the transition element. You now have the lanthanides and actinides, the inner transition element separated out again. Then you now have from 13 to 18 the normal elements and all that. So in the long form of the periodic, in the long form of the modern periodic table, there's no A and B designation. That's the summary of what I'm trying to say. There's no A and B designation. And the numbering is Arabic numeral, because you have to note all this difference and all that. Then again, when it now comes to the number of periods, you have 7 periods in the old one, in the short form of the periodic table, and eight groups. While as in the long form of the periodic table, you equally have 7 periods, but 18 groups and all that. So that's that I'm still using these to, because it was the International Union of Applied Chemists that came out. They are the one that came out with this long form of the periodic table to make it more, more explanatory and easy to comprehend and all that. So I said in this, we want to look at the difference between the short form of the periodic table. I think there's some other things I wrote here. I'm just trying to make sure I'm not forgetting anything or whatever. But then let's just move forward. We want to look at the difference. Okay, I said in the long form of the periodic table, the alkali metals and non-alkaline earth metals, group 1, that's group 1 and group. The alkali metals and the alkali metals is found in group 1, then the alkaline earth metals are found in group 2. Then the transition and inner transition elements make up groups 3 to 12. Then you have groups 13 to 16, which are still the normal elements. Then you now have group 17 as the halogens. Then the noble gases that used to be in group 8 before are now in group 18 here. Then I said you have a set of 15 elements, starting from barium atomic number 56. That is here. From this, after this barium, starting from this one that is called lanthanum 57 to after 57, you can see, I don't know if you're seeing this, after this 57, you see the one that is following it below. You see elements that are in yellow below, which has an atomic number of 58, like that. You have 59, 60, 61, up to 71. From this lanthanum to this element, deuterium 71, are called the lanthanides. Then from this element, 89, AC, 89, I don't know if you're seeing it, actinide. That's the name, actinum rather. To this, the next element, which is 90, thorium. These are all radioactive elements. To 103, because what we have up to this 103, these are called the actinides. So both this lanthanide, actinide, they all make up the inner transition elements. So the elements of the periodic table are divided into the normal elements, the transition elements, and the inner transition elements. That's what I'm trying to say. So I hope you got that clear. So we now want to look at the difference. What's the difference? What's the conclusion we're going to draw, or what you take home? Now, the difference between the short form of the periodic table and the long form of the periodic table is this. The short form of the periodic table has 8 vertical columns, while the long form has 18 vertical columns. Remember that these vertical columns are called groups. Then for the short form, what was used was Roman numerals, while for the long form, the numbering of the groups is the Arabic numerals. The normal way we write our 1, 2, 3. That's what is called Arabic numeral. Then for the short form of the periodic table, you have mixtures of A and B subgroups, that is the normal and transition elements together in a group, while for the long form, there's separation of the normal elements from the transition and inner transition element. So that is that about the long form of the periodic table. I want to take the last unit, the last topic, which is nomenclature of elements having Z. Anywhere you see Z in chemistry, is atomic number. Capital Z means atomic number. So this is how it is in your course material. So it's simply telling you that this is nomenclature of element having atomic number greater than 100. Because why this is so, you know, the way element, because you should have asked yourself or wondered, how are these elements named? Most of these elements that were discovered were named according to who discovered them, or according to countries. You even have Americanium, an element called like that. Other one is this Kosovo, whatever, one of those elements in one of those states in Russia and all that. So some countries, based on if the discoverer, the scientists came from their country, they name it after their country. Some after the scientists and things like that. And at times, you have scientists that are working independent of each other. That means, when I say independent, you know what I mean? Independent. They are not together. You might, for instance, now, I might be here in Abuja, in the lab, synthesizing something, and I discover an element. Another somebody somewhere, maybe in Ghana, at the same time, divine providence, we discover the same thing at the same time. And then, of course, when you discover, like today, I was in a conference, Chemical Society of Nigeria, I've been in a conference and all that, where every research that chemists have, you go to present it. I did my presentation today and all that. So when people discover things or do their research, they go to present it to their fellow scientists so that they can criticize and add or whatever. So maybe as they now come together, they are presenting the same thing. Then the person will say, no, you copy from me. It's me that discovered it first. No, it is me. How can you say it's me? But they didn't copy from each other. It was just independent discovery and all that. Now there's tussle. Even at times it leads to what? The countries begin to fight. They want to steal. Because it's just here in Nigeria. They are not serious with science. The world has left us. Outside there, the Western world don't joke with science. They don't joke with discovery and all that because they know what they do with it and how they can advance the world with it. So if they begin to quarrel, countries begin to fight. No, it's our own scientists. It belongs to us and all that. So in order to avoid all those problems, the International Union of Pure and Applied Sciences now said, okay, there has to be a way of naming these elements until it is proven, well proven, that truly an element has been discovered and this is whom, before they can now allow that person can name it either after him or her or after his or her own country. So that's why this nomenclature of elements, why they say nomenclature of elements having atomic number greater than 100, because we have over more than 400 elements that have been discovered. So we're not saying below, it's above. Because if you look at the periodic table, let me take you back there. Just look at, you even say 118. So the 118th element has been discovered. So that's why, and this is how they were all named first using this nomenclature before it was ascertained that, yes, is this person truly is an element, truly is correct, and is this person or is this, or you want to use his name or you want to use the name of the country before it's allowed and all that. So that's why they are teaching you this nomenclature of elements having atomic number greater than 100. So how do we name these elements? First and foremost, we use what we call the root and the suffix. Now, let me just use simple terms without speaking too much grammar here. He said the name of the element is derived directly from the atomic number of the element using the following numerical roots. We have said elements more than 100, atomic number of 100 has been discovered. So they are saying you begin with, there's a way 1 to 9 has been named. 0 means nil, N-I-L. 1 is un, 2, by. 3, try. 4, quad. 5, pent. 6, hence. 7, sept. 8, oct. Then 9, N-E-N-N. So you use these numerical roots. Now, for example, we have an element, assuming I just discovered an element, or you just discovered an element with atomic number 1, that's 101. How do we now name it first? Because you cannot just be saying, I've just discovered an element with atomic number 101. It has to have a name. So, and you know, everything has to be systematic, because International Union of Applied Science is a scientific body, and science is about systematic way of doing things. So you have to follow that systematic way. And that's what they're saying, that the systematic way is like this. So now, I've been told that 1 means NIL, nil. So it means I'll put that nil first. I've been told that 0 is UN. It means I should put un. Then after that, I put that 1 again, nil. He said the roots are put together in order of the digits which make up the atomic number and terminated by IUM to spell out the name. So I've just put them together. I think I continued somewhere here. Okay, but you've just seen basically what I did. So by the time, let me see if I can type here. This was this nil, N-I, like this. I think you're seeing me. Okay, you can't even talk. Then 0, sorry. 1 is So I'm following it, Then the next one is O, N-I-L, nail. Put N-I-L, nail. The next one, to make the 101, is another 1. So I put UN. I now end it with IUM. So I put my IUM. This now becomes the name of this element. Unilunium. Unilunium. That is it. So that is how it is named. But this is a simpler one, because let's look at the other scenario. We said the final N of EN is omitted. I said, remember, N is 9. That's ENN is 9. You said the final N of EN of 9 is omitted. This thing is EN. Remember, EN is 9. So the final N of 9, that's N, ENN, is omitted when it occurs before 0. I don't know if you're seeing that, but what I mean is before 0. That's why I said, for example, I have 190. So if I'm told that I have to omit, the final N. So now, if we do this, I don't know if you can see me, going by the numerical root, on or on is 1. This is what I will have. Then the next one is 9. 9 is ENN. I put ENN. But I'm told, because the next one is 0. So they say if this 9 comes before 0, I should remove the last N of that 9, of that N. So I remove it. Then what is 0? 0 is NIL, nail, or nil, anyhow you want to put it, NIL. I put it. Then remember, I'm told to end it with IUM. So I now end it. This becomes the name of this element. Unenilium. This is what it is. So you just follow this systematic way of naming, and you now get it. That's one stage. So I've just done that. There's another scenario where it is, where you have to remove the I, where you have to remove the I. Now, we said there's another scenario. He said the final I of by, remember by is 2 and try is 2, is omitted when it occurs before IUM, before the final thing. Let's say, for example, I want to name the element I want to name the element 121, 121. I follow the rule. I put on for 1. On. 2 is by. Okay, I think that will do better by me having 2. I put bi. I have another 2, bi. But I'm told that if I have an I before the ending prefix, IUM, I should remove that I. So I remove it, I put IUM. So I now have un by biome. I take another example with 1, 2, 3, because 3 try ends with 1. So it's going to be, I do the same thing. On. 2 is by, I put by. Then 3 is try, I put TRI. Now I have to put the ending word there, or the ending suffix. But I'm told that if the I comes before that IUN, I should remove the I. So I remove it. So I have IUN. This becomes by triumph. That becomes the name of the element. Maybe I should save this and leave it there and all that. So that is how to name, elements. These are some examples that I did, but I've already taught you online. So at this junction, I would stop to share and mute you so that you can ask your question. Hello? Hello? Okay. Hello?
Hello.
We can hear you, ma.
We can hear you,
Okay.
ma.
Okay.
Hello, ma'am.
Yes, I'm listening. Before you talk, you raise up your hand. Okay, talk. Who is talking? This is
Emmanuel.
Okay.
Ma'am, this method of naming the elements, they are only effective if are they only effective that is after 100?
How can they be? They said from when they say something is from 100 and above, it means even to 500, even to 1,000.
Yes, that's what I mean.
For example,
100 above, so which means it is not effective for below 100.
It is not because, remember, I think you were listening, all the elements below 100 have been discovered. I showed you the periodic table again, that even up to the 118th element have been discovered and all that. So they're just talking about how to name elements that are newly discovered, because any element you are talking now is from above 100.
Okay, ma'am. Thank you, ma'am.
Any other question?
Yes, ma'am.
This from credit to every person. You're correct. That's what I just told you. So let me just answer him. Okay. Okay, let me take questions. I don't know whether these are the people that raised hand before. More Bayo. Is this something like that?
Yes, ma'am. Good evening, ma'am.
Okay.
So that means there's a possibility that we can discover elements that will be up to, let's say, 900 and something, yeah?
If the atomic number gives you that.
Yeah.
Yes.
Yeah. Okay. Thank you, ma'am.
You're welcome. Any other person?
Yes, ma'am. Please, can you shed more light on how to remove the I
how to remove the I.
Yes.
I said, when you know, okay, tell me those numbers that have I in them. You remember?
Yes,
We
ma'am.
have try, we have die.
We have 0 and 3.
No, 0 is
Try, we have die.
NIL. Nil. NIL.
Okay. 2 and 3.
2 and 3.
2 and 3.
Yes. So we're saying that if that number, if you have that, then before you end, remember you have to end with IUM. Because you cannot be having, like, for instance, now, by, B-I, now begin to put IUM, double I. Have you seen many details like that? No. That's why they say you remove that I in by or 3. So you just leave it as B or 2, T or 3, then you put your IUM.
Okay.
There's somebody crowded. There's something, sorry, let me just help somebody out. There's that is crowded something. He wrote 999 and he put EN and whatever. I don't know if it's now that you are coming, because that's what I was trying to. Okay, okay. Asuku, Rachel have done it. Fine. So crowded, follow it. It's when okay, any other person. You remove that. Sorry, let me. Sorry, let me just. You crowded. I don't know what's your reading. You remove the second, the last N in N. That is 9. ENN. You remove that last N when that 9 is before a 0. That's you get them. That's why I use 190. When you look at 190, you know you will get 9 before the 0. So you now
okay,
you have
ma.
to.
Okay, ma. Okay, ma. It's crowned.
Yes. Okay. Okay. So any other person, sorry, we call it a day. I've spent how many hours here?
Yes, ma'am, I have a question, please.
Okay, go ahead. Go ahead.
Please, ma'am, my question is, if, for instance, now, someone discovered elements, and you want to name it, since the element discovered
You say, and you want to do what?
Name it. You want to name it.
Yes.
You want to name the elements. And the element that has been discovered ended with 118. So the next one, for instance, when I discovered an element now, I want to number it. Will I number it from 119, or I have to number it the way that?
Listen. For you to say you discovered an element, is it just because you just saw one thing like that, you now say you discovered? It is based on scientific laboratory analysis. In the lab, you test for physical properties. You test for chemical properties. In those testing for physical properties, you would have to determine the atomic number. You have to know the number of protons that it contains. From the number of protons and the number of neutrons, you will now know the atomic weight. Then from that number of atomic number, you can now know. Remember, in the periodic table, elements are arranged in order of atomic number. And now, in the modern periodic table we have, where they are discovered elements with the last one, atomic number 118. So you have to determine the atomic number. So it's the atomic number that would help you to know how to name it. For instance, you discovered an element with atomic number 120. Remember, you cannot just come and begin to say you discovered it. Scientists will have to test, because you did this thing, not accidentally in the lab or however, but that accidentally it was even through analysis that it was known. And we're saying science is universal. That's why we're rejecting a lot of classification, because when they check it and test it, it is not working according to the principles of science. It will be dropped. So if you say you have discovered something, like I told you, I'm just coming from I just finished a workshop where I went to present my research in the conference of the Chemical Society of Nigeria. I've done a research, I came out with something, I need to present it. And I explained you why I did it scientifically, following what I did. They will criticize it and tell you whether you're right or not, whether they accept it or not, before they can publish it and all that. So that is it. So that's why, otherwise, even that of Antonio Laverse, they will have just accepted this classification. No, it will be tested. So if you now say you discovered an element, and in the researching in the method of trying to determine number of proton, number of electrons, atomic weight, you followed all those things scientifically. You gave this. Other scientists all over the world will check it. They will follow that same procedure, and once it's given the same result, okay, it's agreed. But as you're going to present it, you have to give it a name. That's why the International Union of Applied Science is saying, follow this systematic way. Name it like that first, before it will be tried. When it's tried and you're satisfied, then if you can now later on, if you want to give it your name, of course, if I discover something, I'll give it my name after it has been accepted by scientists. Now, give it your name. Or if you love your country too much, you want to name it after your country, as so many scientists did. Even your country can pay you money for you to name it after them, because these things, there's a lot in it. It's just in Nigeria, because we don't know values. Some countries will take up the name. So that's why I was saying that what initiated this naming was because of a lot of controversy when elements were discovered. Some scientists working at the same time came out discovering at the same time. It became problem. Whose name will it answer? Even the countries now came into, no, this scientist in my country, it's almost even causing war. That's why they're saying, no, do it like this. Then when we now test it that way, this person, the person that is owned is more acceptable, we agree and go with that person. You understand what I'm saying? The basis of all this naming. Are we together?
Yes, ma'am.
Yes, ma, it's very clear.
And if you just follow that, if you follow that procedure, the only thing you just have to know, just know those numerical rules. Nil, zero, by, try, you know, all those stuff, when you know it, then this before this, and if this, those things you can name even to 5,000, even when they say the thing is 5,000, you will name it. And just know the difference between the short form and the long form periodic table. And then know there's a difference between Mendeleev periodic law, Mendeleev periodic table, and the new periodic table, and the modern, or let me say the modern periodic table and the modern periodic law. Just know those differences, and you're good to go. All right. I've stayed 2 hours here with you, but I'm not complaining because it's my pleasure. So the way it appears from the setting of the platform, it appears is twice a week, Tuesday and Thursday by 5. Because remember when we met on Thursday, I said we will meet. When we met on Tuesday, I said we'll meet on when was that? Thursday, 7 to 8. I came online, but no permission. Thursday, I now saw Friday, 5 to 6. 2,000 ahead. That's it. Okay, okay, this thing has gone up. I can't see it again. All right. Good night, and take care of yourself. We'll see you again on Tuesday, 5 to 6. And remember, as I said, in case of those coming for the first time, that throughout this semester, it is that link and passcode you'll be using to enter. Bye, and take care of yourself.
Bye-bye. Thank you, ma'am.
Thank you. Bye.